Let's talk vision subsystem. This is the eyes of our robot. Without it, our robot would be as clueless as a cat in a laser pointer factory. The vision system is where everything starts. It's literally the only sensor we have, so if it sees it, we all see it. It's responsible for spotting shelves, items, obstacles, road markers, you name it. Think of it like our robot's radar, GPS, and guide dog all rolled into one. With a Raspberry Pi camera module V2, we've got 8 megapixels of crisp vision. But here's the real magic. We use multi-threading to keep things running smoothly. One thread captures images while another processes them in real time, at all over 10 frames per second, even sometimes up to 20 frames per second. This means that our bot can calculate object distances, angles, and even avoid obstacles fast and accurately. Our HSV color thresholding lets it identify blue shelves, green obstacles, and orange items quickly. It passes all this information to navigation, giving our bot precise awareness in every move. In short, the vision system is quick, sharp, and absolutely essential for keeping our robot on track and collision-free every step of the way.
Okay, time for the item collection system. So with the item collection system, we broke it into two different components, the lifting system and the actual gripping system. So with the lifting system, we went through a couple of different design changes. We started off as a scissors lift, but through design flaws, we found out that it was easier to go with an angular lifting design as seen in some construction equipment. So with that, we used a 3 kilogram per centimeter torque servo motor that would then directly drive the arm up to lift the gripping system. In that, there would be a second member not directly attached to the servo that would constrain the gripping system to keep it level. With the gripping system, we used a design that would clasp around and conform to the shape of the item in order to softly grip it and hold it without it dropping and without damaging the item. To do this, we would have one solid arm coated in a very soft material that would remain stationary. We would then have another arm attached to a lead screw spun by a small servo motor, and as that would spin, it would bring it in close, pushing in the item into the soft material spun.
What's up everyone, my name is Ethan, and I had the privilege of being in charge of navigation for our project. Navigation is a critical aspect of our robot's functionality. It requires the integration of all the subsystems to achieve effective movement within a complex warehouse environment. One of our primary challenges is obstacle avoidance. While we weren't able to fully implement this feature, the robot successfully avoided obstacles in most stages during its navigation. This feature was limited by the placement of the camera and size of the robot. However, this was still a significant achievement that helped us enhance the robot's operational safety. To guide the robot through the warehouse, we employed a reflex agent that utilized a state machine making use of object-oriented programming. This design enabled the robot to make quick decisions in response to its changing environment, enhancing its overall navigational capabilities and efficiency. The method utilized to achieve this is known as potential fields, which utilizes inputs from the vision system, such as range, bearing, and area, which also played a large part in centering the robot on items and determining its movement trajectory. This approach allowed the robot to dynamically interpret its environment and respond to various inputs, which is essential for navigating around obstacles and the warehouse environment effectively.
Into the mobility system, I wanted something that wouldn't just move, it would conquer. Then what option did I have other than tank treads? Jokes aside, these actually provided excellent grip on uneven and inclined surfaces. We used 75:1 carbon brushed motors, which would be controlled by a Raspberry Pi motor hat, which had motor and servo control functionality. These motors were great to carry a 1 kilogram weight up a 15-degree incline while also being able to obliterate the minimum and maximum speed requirements. A move function was implemented that would control these motors with a linear and angular velocity, which consisted of a PID controller that would read the actual motor speed and compare it with the inputted speed and try to minimize the error between the two. The power system of the robot consisted of this PCB, which had an inbuilt voltage regulator that would power the servos and the motor hat, and an external buck converter which would power the Raspberry Pi itself. We had switch and state LEDs at the back of the PCB so that it looks more aesthetically pleasing and cleaner. So that, my friends, was the gist of the mobility system of the robot.